So hello and welcome to lesson 3 of Practical Deep Learning for Coders. We were looking at getting our model into production last week. And so we're going to finish off that today, and then we're going to start to look behind the scenes at what actually goes on when we train a neural network. We're going to look at kind of the math of what's going on. And we're going to learn about SGD and some important stuff like that. The order is slightly different to the book. In the book, there's a part in the book which says like, hey, you can either go to lesson 4 or lesson 3 now, and then go back to the other one afterwards. So we're doing lesson 4 and then lesson 3, chapter 4 and then chapter 3, I should say. You can choose it whichever way you're interested in. Chapter 4 is the more technical chapter about the foundations of how deep learning really works, whereas chapter 3 is all about ethics. And so for the lessons, we'll do that next week. We're looking at 02 production notebook. And we're going to look at the fast book version, the one with, in fact, everything I'm looking at today will be in the fast book version. Remember last week we had a look at our bears, and we created this data loaders object by using the data block API, which I hope everybody's had a chance to experiment with this week. If you haven't, now's a good time to do it. We kind of skipped over one of the lines a little bit, which is this item transforms. So what this is doing here when we said resize, the images we downloaded from the internet are lots of different sizes and lots of different aspect ratios. Some are tall and some are wide, some are square and some are big, some are small. When you say resize for an item transform, it means each item, so an item in this case is one image, is going to be resized to 128 by 128 by squishing it or stretching it. And so we had a look at, you can always say show batch to see a few examples. And this is what they look like. Squishing and stretching isn't the only way that we can resize. Remember, we have everything, we have to make everything into a square before we kind of get it into our model. By the time it gets to our model, everything has to be the same size in each mini batch. So that's why, and making it a square is not the only way to do that, but it's the easiest way, and it's by far the most common way. Another way to do this is we can create another data block object, and we can make a data block object that's an identical copy of an existing data block object, where we can then change just some pieces. And we can do that by calling the new method, which is super handy. And so let's create another data block object, and this time with a different item transform, where we resize using the Squish method.
We have a question. What are the advantages of having square images versus rectangular ones?
That's a great question. So really it's simplicity. If you know all of your images are rectangular of a particular aspect ratio to start with, you may as well just keep them that way. But if you've got some which are tall and some which are wide, making them all square is kind of the easiest. Otherwise, you would have to kind of organize them such as all of the tall ones kind of ended up in a mini batch and all of the wide ones ended up in a mini batch. And then you'd have to kind of then figure out what the best aspect ratio for each mini batch is. And we actually have some research that does that in FastAI2, but it's still a bit clunky. I should mention, okay, I just lied to you. The default is not actually to squish or stretch. The default, I should have said, sorry, the default when we say resize is actually just to grab the center. So actually all we're doing is we're grabbing the center of each image. So if we want to squish or stretch, you can add the resize method.squish argument to resize. And you can now see that this black bear is now looking much thinner, but we have got the kind of leaves that are around on each side, for instance.
Another question. When you use the DLS.new method, what can and cannot be changed? Is it just the transforms?
So it's not dls.new, it's bears.new, right? So we're not creating a new data loaders object, we're creating a new data block object. I don't remember off the top of my head, so check the documentation, and I'm sure somebody can pop the answer into the forum. You can see when we use .squish that this grizzly bear has got pretty kind of wide and weird looking, and this black bear has got pretty weird and thin looking. And it's easiest kind of to see what's going on if we use Resized method.pad. And what .pad does, as you can see, is it just adds some black bars around each side. So you can see the grizzly bear was tall. So then when we stretched, squishing and stretching are opposites of each other. So when we stretched it, it ended up wide. And the black bear was originally a wide rectangle, so it ended up looking kind of thin. You don't have to use zeros. Zeros means pad it with black. You can also say like reflect to kind of have the pixels will kind of look a bit better that way if you use reflect. All of these different methods have their own problems. The pad method is kind of the cleanest. You end up with the correct size. You end up with all of the pixels, but you also end up with wasted pixels. So you kind of end up with wasted computation. The squish method is the most efficient because you get all of the information, and nothing's kind of wasted. But on the downside, your neural net's going to have to learn to kind of like recognize when something's been squished or stretched. And in some cases, it wouldn't even know. So if there's two objects you're trying to recognize, one of which tends to be thin and one of which tends to be thick, and otherwise they're the same, they could actually be impossible to distinguish. And then the default cropping approach actually removes some information. So in this case, this grizzly bear here, we actually lost a lot of its legs. So if figuring it out what kind of bear it was required looking at its feet, well, we don't have its feet anymore. So they all have downsides. So there's something else that you can do, a different approach, which is instead of to say resize, you can say random resized crop. And actually this is the most common approach. And what random resized crop does is each time it actually grabs a different part of the image and kind of zooms into it, right? So this is all the same image, and we're just grabbing a batch of 4 different versions of it. And you can see some are kind of, they're all squished in different ways, and we've kind of selected different subsets and so forth. Now, this kind of seems worse than any of the previous approaches because I'm losing information. Like this one here, I've actually lost a whole lot of its back, right? But the cool thing about this is that, remember, we want to avoid overfitting. And when you see a different part of the animal each time, it's much less likely to overfit because you're not seeing the same image on each epoch that you go around. That makes sense? So this random resized crop approach is actually super popular. And so min scale 0.3 means we're going to pick at least 30% of the pixels of kind of the original size each time. And then we'll kind of like zoom into that square. So this idea of doing something so that each time the model sees the image, it looks a bit different to last time, is called data augmentation. And this is one type of data augmentation. It's probably the most common, but there are others. One of the best ways to do data augmentation is to use this org transforms function. And what org transforms does is it actually returns a list of different augmentations. And so there are augmentations which change contrast, which change brightness, which warp the perspective. So you can see in this one here, it looks like this bit's much closer to you and this bit's much away from you because it's kind of been perspective warped. It rotates them. See, this one's actually been rotated. This one's been made really dark, right? These are batch transforms, not item transforms. The difference is that item transforms happen one image at a time. And so the thing that resizes them all to the same size, that has to be an item transform. Pop it all into a mini batch, put it on the GPU, and then a batch transform happens to a whole mini batch at a time. And by putting these as batch transforms, the augmentation happens super fast because it happens on the GPU. And I don't know if there's any other libraries as we speak which allow you to write your own GPU accelerated transformations that run on the GPU in this way. So this is a super handy thing in fastai too. So you can check out the documentation for org transforms, and when you do, you'll find the documentation for all of the underlying transforms that it basically wraps, right? So you can see if I shift tab, I don't remember if I've shown you this trick before. If you go inside the parentheses of a function and hit shift tab a few times, it'll pop open a list of all of the arguments. And so you can basically see, you can say like, oh, can I sometimes flip it left, right? Can I sometimes flip it up, down? What's the maximum amount I can rotate, zoom, change the lighting, warp the perspective, and so forth.
How can we add different augmentations for train and validation sets?
So the cool thing is that automatically fastai will avoid doing data augmentation on the validation set. So all of these org transforms will only be applied to the training set, with the exception of random resized crop. Random resized crop has a different behavior for each. The behavior for the training set is what we just saw, which is to randomly pick a subset and kind of zoom into it. And the behavior for the validation set is just to grab the center, the largest center square that it can. You can write your own transformations. They're just Python. They're just standard PyTorch code. The way, if you, and by default, it will only be applied to the training set. If you want to do something fancy like random resized crop, where you actually have different things being applied to each, you should come back to the next course to find out how to do that, or read the documentation. It's not rocket science, but it's not something most people need to do. Okay, so last time we here did bears.new with a random resized crop, min scale of 0.5. We added some transforms. And we went ahead and trained. Actually, since last week, I've rerun this notebook. It's on a different computer, and I've got different images, so it's not all exactly the same. But I've still got a good confusion matrix. So of the black bears, 37 were classified correctly, 2 were grizzlies, 1 was a teddy. Now, and we talked about plot top losses. And it's interesting, you can see in this case, there's some clearly kind of odd things going on. This is not a bear at all. This looks like it's a drawing of a bear, which is decided is predicted as a teddy, but this thing's it's meant to be a drawing of a black bear. I can certainly see the confusion. You can see how some parts of it are being cut off. We'll talk about how to deal with that later. Now, one of the interesting things is that we didn't really do much data cleaning at all before we built this model. The only data cleaning we did was just to validate that each image can be opened. There was that verify images call. And the reason for that is it's actually much easier normally to clean your data after you create a model. And I'll show you how. We've got this thing called image classifier cleaner, where you can pick a category, right? And training set or validation set. And then what it will do is it will then list all of the images in that set, and it will pick the ones which which is the least confident about, which is the most likely to be wrong, where the loss is the worst, to be more precise. And so this is a great way to look through your data and find problems. So in this case, the first one is not a teddy or a brown bear or a black bear, it's a puppy dog, right? So this is a great cleaner because what I can do is I can now click delete here. This one here looks a bit like an Ewok rather than a teddy. I'm not sure. What do you think, Rachel? Is it an Ewok? I'm going to call it an Ewok, right? And so you can kind of go through Okay, that's definitely not a teddy. And so you can either say like, oh, that's wrong, that's actually a grizzly bear, or it's wrong, it's a black bear, or I should delete it, or by default just keep it, right? And you can kind of keep going through until you think like, okay, they all seem to be fine. Maybe that one's not. And kind of once you get to the point where they all seem to be fine, you can kind of say, okay, probably all the rest are fine too, because they all have lower losses, so they all fit the kind of the mold of a teddy. And so then I can run this code here, where I just go through cleaner.delete. So that's all the things which I select to delete for, and unlink them. So unlink is just another way of saying delete a file. That's the Python name. And then go through all the ones that we said change, and we can actually move them to the correct directory. If you haven't seen this before, you might be surprised that we've kind of created our own little GUI inside Jupyter Notebook. Yeah, you can do this. And we built this with less than a screen of code. You can check out the source code in the fastai notebooks. So this is a great time to remind you that fastai is built with notebooks. And so if you go to the fastai repo and clone it, and then go to NBs, you'll find all of the code of fastai written as notebooks. And they've got a lot of pros and examples and tests and so forth. So the best place to learn about how this is implemented is to look at the notebooks rather than looking at the module code. Okay. By the way, sometimes you'll see like weird little comments like this. These weird little comments are part of a development environment for Jupyter Notebook we use called NBDev, which we built. So Silva and I built this thing to make it much easier for us to kind of create books and websites and libraries in Jupyter Notebooks. So this particular one here, hide, means when this is turned into a book or into documentation, don't show this cell. And the reason for that is because you can see I've actually got it in the text, right? But I thought when you're actually running it, it would be nice to have it sitting here waiting for you to run directly. So that's why it's shown in the notebook, but not in the book. It's shown differently. And you'll also see these things like S: with a quote. In the book, that would end up saying Sylvain says, and then what he says. So there's kind of little bits and pieces in the notebooks that just look a little bit odd, and that's because it's designed that way in order to show, in order to create stuff in the book. Right. So then last week we saw how you can export that to a pickle file that contains all the information for the model. And then on the server where you're going to actually do your inference, you can then load that saved file, and you'll get back a learner that you can call predict on. So predict perhaps the most interesting part of predict is the third thing that it returns, which is a tensor, in this case containing 3 numbers. The 3 numbers, there's 3 of them because we have 3 classes: teddy bear, grizzly bear, and black bear, right? And so this doesn't make any sense until you know what the order of the classes is, kind of in your data loaders. And you can ask the data loaders what the order is by asking for its vocab. So a vocab in fastai is a really common concept. It's basically any time that you've got like a mapping from numbers to strings or discrete levels, the mapping is always stored in the vocab. So here, this shows us that the activation for black bear is 10e neg 6. The activation for grizzly is 1. And the activation for teddy is 10e neg 6. So very, very confident that this particular one, it was a grizzly. Not surprisingly, this was something called grizzly.jpg. So you need to kind of know this this mapping in order to display the correct thing. But of course, the data loaders object already knows that mapping, and it's all the vocab, and it's stored in with the loader. So that's how it knows to say grizzly automatically. So the first thing it gives you is the human readable string that you'd want to display. So this is kind of nice that with fastai 2, you save this object, which has everything you need for inference. It's got all the information about normalization, about any kind of transformation steps, about what the vocab is, so it can display everything correctly. Right. So now we want to deploy this as an app. Now, if you've done some web programming before, then all you need to know is that this line of code and this line of code, so this is the line of code you would call once when your application starts up, and then this is the line of code you would call every time you want to do an inference. And there's also a batch version of it, which you can look up if you're interested. This is just to do one at a time. So there's nothing special if you're already a web programmer or have access to a web programmer. These are, you just have to stick these 2 lines of code somewhere, and the 3 things you get back are the human readable string, if you're doing categorization, the index of that, which in this case is 1, is grizzly, and the probability of each class. One of the things we really wanted to do in this course, though, is not assume that everybody is a web developer. Most data scientists aren't. But gee, wouldn't it be great if all data scientists could at least prototype an application to show off the thing they're working on? And so we've tried to kind of curate an approach, which none of it's stuff we've built, it's really just curated, which shows how you can create a GUI and create a complete application in Jupyter Notebook. So the key pieces of technology we use to do this are IPython widgets, which is always called IPyWidgets, and voila. IPyWidgets, which we import by default as widgets, and that's also what they use in their own documentation, has GUI widgets. For example, a file upload button. So if I create this file upload button and then display it, I see, and we saw this in the last lesson as well, or maybe it was lesson 1, an actual clickable button. So I can go ahead and click it, and it says now, okay, you've selected one thing. So how do I use that? Well, these widgets have all kinds of methods and properties, and the upload button has a data property, which is an array containing all of the images you uploaded. So you can pass that to pio_image.create. And so .create is kind of the standard factory method we use in fastai to create items. And pio_image.create is smart enough to be able to create an item from all kinds of different things. And one of the things it can create it from is a binary blob, which is what a file upload contains. So then we can display it, and there's our teddy, right? So you can see how, cells of Jupyter Notebook can refer to other cells that were created, that were kind of have GUI created data in them. So let's hide that teddy away for a moment. And the next thing to know about is that there's a kind of widget called output. And an output widget is, it's basically something that you can fill in later, right? So if I delete, actually, this part here. So I've now got an output widget. Yeah, actually, let's do it this way around. And you can't see the output widget, even though I said please display it, because nothing is output. So then in the next cell, I can say with that output placeholder, display a thumbnail of the image, and you'll see that the display will not appear here. It appears back here, right? Because that's where the placeholder was. So let's run that again to clear out that placeholder. So we can create another kind of placeholder, which is a label. The label's kind of a something where you can put text in it. So you can give it a value, like, I don't know, please choose an image. Okay, so we've now got a label containing please choose an image. Let's create another button to do a classification. Now this is not a file upload button, it's just a general button. So this button doesn't do anything, right? And it doesn't do anything until we attach an event handler to it. An event handler is a callback. We'll be learning all about callbacks in this course. If you've ever done any GUI programming before, or even web programming, you'll be familiar with the idea that you write a function, which is the thing you want to be called when the button is clicked on, and then somehow you tell your framework that this is the onClick event. So here I go, here's my button run. So I say the onClick event, the button run is to call this code. And this code is going to do all the stuff we just saw. It's going to create an image from the upload. It's going to clear the output, display the image, call predict, and then replace the label with a prediction. So there it all is. Now, so that hasn't done anything, but I can now go back to this classify button, which now has an event handler attached to it. So watch this. Click. Boom. And look, that's been filled in. That's been filled in, right? In case you missed it, let's run these again to clear everything out. Okay, everything's gone. This is please choose an image. There's nothing here. I click classify. Oh, pop, pop. Right? So it's kind of amazing how our notebook has suddenly turned into this interactive prototyping playground for building applications. And so once all this works, we can dump it all together. And so the easiest way to dump things together is to create a VBox. A VBox is a vertical box, and it's just something that you put widgets in. And so in this case, we're going to put the following widgets. We're going to have a label that says select your bear, then an upload button, a run button, an output placeholder, and a label for predictions. So let's run these again just to clear everything out so that we're not cheating. And let's create our VBox. So as you can see, it's just got all the pieces, right? Now we've got, what is our, oh, I accidentally ran the thing that displayed the bear. Let's get rid of that. Okay, so there it is. So now I can click upload. I can choose my bear. Okay, and then I can click classify, right? And notice this is exactly this is like the same buttons as these buttons. They're like two places where we're viewing the same button, which is kind of a wild idea. So if I click classify, it's going to change this label and this label because they're actually both references to the same label. Look, there we are. Okay, so this is our app. Right? And so this is actually how I built that that image cleaner GUI is just using these exact things. And I built that image cleaner GUI cell by cell in a notebook, just like this. And so you get this kind of interactive experimental framework for building a GUI. So if you're a data scientist who's never done GUI stuff before, this is a great time to get started because now you can make actual programs. Now, of course, an actual program running inside a notebook is kind of cool, but what we really want is this program to run in a place anybody can run it. That's where Voila comes in. So Voila needs to be installed. So you can just run these lines to install it. It's listed in the pros. And what Voila does is it takes a notebook and doesn't display anything except for the markdown, the IPython widgets, and the outputs. Right? So all the code cells disappear, and it doesn't give the person looking at that page the ability to run their own code. They can only interact with the widgets. Right? So what I did was I copied and pasted that code from the notebook into a separate notebook which only has those lines of code, right? So, so these are just the same lines of code that we saw before. And so this is a notebook. It's just a normal notebook. And then I installed Voila. And then when you do that, if you navigate to this notebook, but you replace notebooks up here with Voila, it actually displays not the notebook, but just, as I said, the markdown and the widgets. So here I've got my bear classifier, and I can click upload. Let's do a grizzly bear this time. And this is a slightly different version. I actually made this so there's no classify button. I thought it would be a bit more fancy to make it so when you click upload, it just runs everything. But as you can see, there it all is, right? It's all working. So this is the world's simplest prototype, but it's a proof of concept, right? So you can add widgets with drop downs and sliders and charts and everything that you can have in a an Angular app or a React app or whatever. And in fact, there's even stuff which lets you use, for example, the whole Vue.js framework. If you know that, it's a very popular JavaScript framework. The whole Vue.js framework, you can actually use it in widgets, and voila. So now we want to get it so that this this app can be run by someone out there in the world. So the Voila documentation shows a few ways to do that, but perhaps the easiest one is to use a system called Binder. And so Binder is at mybinder.org. And all you do is you paste in your GitHub repository name here, right? And this is all in the book, right? So you paste in your GitHub repo name. You change where it says file, you change that to URL. You can see. And then you put in the path, which we were just experimenting with, right? So you pop that here. And then you say launch. And what that does is it then gives you a URL. So then this URL you can pass on to people. And this is actually your interactive running application. So Binder's free. And so this is anybody can now use this to take their Voila app and make it a publicly available web application. So try it. As it mentions here, the first time you do this, Binder takes about 5 minutes to build your site because it actually uses something called Docker to deploy the whole fastai framework and Python and blah, blah, blah. But once you've done that, that virtual machine will keep running for, as long as people are using it, it'll keep running for a while. That virtual machine will keep running for a while as long as people are using it, and it's reasonably fast. So a few things to note here. Being a free service, you won't be surprised to hear this is not using a GPU. It's using a CPU. And so that might be surprising, but we're deploying to something which runs on a CPU. When you think about it, though, this makes much more sense to deploy to a CPU than a GPU. Just a moment. The thing that's happening here is that I am passing along, let's go back to my app. In my app, I'm passing along a single image at a time. So when I pass along that single image, I don't have a huge amount of parallel work for a GPU to do. So this is actually something that a CPU is going to be doing more efficiently. So we found that for folks coming through this course, the vast majority of the time, they wanted to deploy inference on a CPU, not a GPU, because they're normally just doing one item at a time. it's way cheaper and easier to deploy to a CPU. And the reason for that is that you can just use any hosting service you like, because just remember, this is just a program at this point, right? And you can use all the usuals: horizontal scaling, vertical scaling. You can use Heroku, you can use AWS, you can use inexpensive instances. Super cheap and super easy. Having said that, there are times you might need to deploy to a GPU. For example, maybe you're processing videos, and so like a single video on a CPU to process it might take all day. Or you might be so successful that you have 1,000 requests per second, in which case you could like take 128 at a time, batch them together, and put the whole batch on the GPU and get the results back and pass them back around. I mean, you've got to be careful of that, right? Because if your requests aren't coming fast enough, your user has to wait for a whole batch of people to be ready to be processed. But conceptually, as long as your site is popular enough, that could work. The other thing to talk about is you might want to deploy to a mobile phone. And deploying to a mobile phone, our recommendation is wherever possible, do that by actually deploying to a server and then have a mobile phone talk to the server over a network. Because if you do that, again, you can just use a normal PyTorch program on a normal server and normal network calls. It makes life super easy. When you try to run a PyTorch app on a phone, you're suddenly now not in an environment where like PyTorch will run natively, and so you'll have to like convert your program into some other form. And there are other forms, and the main form that you convert it to is something called ONNX, which is specifically designed for kind of super high speed, high performance, approach that can run on both servers or on mobile phones. And it does not require the whole Python and PyTorch kind of runtime in place. But it's much more complex than not using it. It's harder to debug, and it's harder to set it up, and it's harder to maintain it. So if possible, keep things simple. And if you're lucky enough that you're so successful that you need to scale it up to GPUs and stuff like that, then great. Hopefully you've got the finances at that point to justify, spending money on a ONNX expert or serving expert or whatever. And there are various systems you can use, to like ONNX runtime and AWS SageMaker, where you can kind of say, here's my ONNX bundle, and it'll serve it for you or whatever. PyTorch also has a mobile framework, same idea. So, all right, so you've got, it's kind of funny, we're talking about two different kinds of deployment here. One is deploying like a hobby application, that you're prototyping, showing off to your friends, explaining to your colleagues how something might work, a little interactive analysis. That's one thing, but maybe you're actually prototyping something that you want to turn into a real product. Or an actual real part of your company's operations. When you're deploying, something in real life, there's all kinds of things you've got to be careful of. One example of something to be careful of is, let's say you did exactly what we just did, which actually, this is your homework, is to create your own application. Right? I want you to create your own image search application. You can use my exact set of widgets and whatever if you want to, but better still, go to the IPyWidgets website and see what other widgets they have and try and come up with something cool. Try and show off as best as you can, then show us on the forum. Now, let's say you decided that you want to create an app that would help the users of your app decide if they have healthy skin or unhealthy skin. So if you did the exact thing we just did, rather than searching for grizzly bear and teddy bear and so forth on Bing, you would search for healthy skin and unhealthy skin. Right? So here's what happens, right? And remember, in our version, we never actually looked at Bing. We just use the Bing API, the image search API. But behind the scenes, it's just using the website, right? So if I click healthy, if I type healthy skin and say search, I actually discover that the definition of healthy skin is young white women touching their face lovingly. So that's what your healthy skin classifier would learn to detect, right? And so this is a great example from Deb Raji, and you should check out her paper, Actionable Auditing, for lots of cool insights about model bias. But I mean, here's like a fascinating example of how if you weren't looking at your data carefully, you end up with something that just doesn't at all actually solve the problem you want to solve. This is tricky, right? Because the data that you train your algorithm on, if you're building like a new product that didn't exist before, by definition, you don't have examples of the kind of data that's going to be used in real life, right? So you kind of try to find some from somewhere, and if you do that through like a Google search, it's pretty likely you're not going to end up with a set of data that actually reflects the kind of mix you would see in real life. You know, the main thing here is to say be careful, right? And in particular for your test set, you know, that final set that you check on, really try hard to gather data that reflects the real world. So like just, you know, for example, for the healthy skin example, you might go and actually talk to a dermatologist and try and find like 10 examples of healthy and unhealthy skin or something. And that would be your kind of gold standard test. There's all kinds of issues you have to think about in deployment. I can't cover all of them. I can tell you that this O'Reilly book called Building Machine Learning Powered Applications is a great resource. And this is one of the reasons we don't go into detail about A/B testing and when should we refresh our data and how do we monitor things and so forth, is because that book's already been written, so we don't want to rewrite it. I do want to mention a particular area that I care a lot about, though, which is, let's take this example. Let's say you're rolling out this bear detection system, and it's going to be attached to video cameras around a campsite. It's going to warn campers of incoming bears. So if we used a model that was trained with that data that we just looked at, you know, those are all very nicely taken pictures of pretty perfect bears, right? There's really no relationship to the kinds of pictures you're actually going to have to be dealing with in your campsite bear detector, which it's going to have video and not images. It's going to be nighttime. It's going to be probably low resolution security cameras. You need to make sure that the performance of the system is fast enough to tell you about it before the bear kills you. You know, there will be bears that are partially obscured by bushes or in lots of shadow or whatever, none of which are the kinds of things you would see normally in like internet pictures. So what we call this out-of-domain data. Out-of-domain data refers to a situation where the data that you are trying to do inference on is in some way different to the kind of data that you trained with. And this is actually, there's no perfect way to answer this question. And when we look at ethics, we'll talk about some really helpful ways to minimize how much this happens. For example, it turns out that having a diverse team is a great way to kind of avoid being surprised by the kinds of data that people end up coming up with. But really, it's just something you've got to be super thoughtful about. Very similar to that is something called domain shift. And domain shift is where maybe you start out with all of your data is in domain data, but over time, the kinds of data that you're seeing changes. And so over time, maybe raccoons start invading your campsite, and you weren't training on raccoons before it was just a bear detector. And so that's called domain shift. And that's another thing that you have to be very careful of. Rachel, was your question?
No, I was just going to add to that in saying that all data is biased, so there's not kind of a form of debiased data or perfectly representative in all cases data, and that a lot of the proposals around addressing this have kind of been converging to this idea that you see in papers like Timnit Gebru's data sheets for data sets of just writing down a lot of the details about your data set and how it was gathered and in which situations it's appropriate to use and how it was maintained. And so that's not that you've totally eliminated bias, but that you're just very aware of the attributes of your data set so that you won't be blindsided by them later. And there have been kind of several proposals in that school of thought, which I really like around this idea of just kind of understanding how your data was gathered and what its limitations are.
Thanks, Rachel. So a key problem here is that you can't know the entire behavior of your neural network. With normal programming, you typed in the if statements and the loops and whatever. So in theory, you know what the hell it does, although it's still sometimes surprising. In this case, you didn't tell it anything. You just gave it examples to learn from and hoped that it learned something useful. There are hundreds of millions of parameters in a lot of these neural networks, and so there's no way you can understand how they all combine with each other to create complex behavior. So really, like, there's a natural compromise here, is that we're trying to get sophisticated behavior. So like recognizing pictures, sophisticated enough behavior we can't describe it. And so the natural downside is you can't expect the process that the thing is using to do that to be describable for you to be able to understand it. So our recommendation for kind of dealing with these issues is a very careful deployment strategy, which I've summarized in this little graph, this little chart here. The idea would be, first of all, whatever it is that you're going to use the model for, start out by doing it manually. So have a park ranger watching for bears, have the model running next to them, and each time the park ranger sees a bear, they can check the model and see, like, did it seem to have picked it up? So the model's not doing anything. There's just a person who's like running it and seeing would it have made sensible choices. And once you're confident that it makes sense, that what it's doing seems reasonable, in as close to the real life situation as possible, then deploy it in a time and geography limited way. So pick like one campsite, not the entirety of California, and do it for, 1 day, and have somebody watching it super carefully, right? So now the basic bear detection is being done by the bear detector, but there's still somebody watching it pretty closely, and it's only happening in one campsite for 1 day. And so then, as you say, like, okay, we haven't destroyed our company yet, so let's do 2 campsites for a week, and then let's do, the entirety of Marin for a month, and so forth. So this is actually what we did when I used to be at this company called Optimal Decisions. Optimal Decisions was a company that I founded to do insurance pricing. And if you change insurance prices by, 1% or 2 in the wrong direction, the wrong way, you can basically destroy the whole company. This has happened many times. Insurers are companies that set prices. That's basically the product that they provide. So when we deployed new prices for Optimal Decisions, we always did it by saying okay, we're going to do it for 5 minutes for everybody whose name ends with a D. So we'd kind of try to find some group which hopefully would be fairly, they would all be different, but not too many of them. And we'd gradually scale it up, and you've got to make sure that when you're doing this, that you have a lot of really good reporting systems in place that you can recognize, are your customers yelling at you? Are your computers burning up? Are your computers burning up? Are your costs spiraling out of control, and so forth? So it really requires great reporting systems.
Does FastAI have methods built in that provide for incremental learning, i.e. improving the model slowly over time with a single data point each time?
Yeah, that's a great question. So this is a little bit different, which is this is really about dealing with domain shift and similar issues by continuing to train your model as you do inference. And so the good news is you don't need anything special for that. It's basically just a transfer learning problem. So you can do this in many different ways. Probably the easiest is just to say like, okay, each night, each night, at midnight, we're going to set off a task which grabs all of the previous day's transactions as mini batches and trains another epoch. And so, yeah, that actually works fine. You can basically think of this as a fine-tuning approach where your pre-trained model is yesterday's model and your fine-tuning data is today's data. So as you roll out your model, one thing to be thinking about super carefully is that it might change the behavior of the system that it's a part of. And this can create something called a feedback loop. And feedback loops are one of the most challenging things for real-world model deployment, particularly of machine learning models, because they can take a very minor issue and explode it into a really big issue. So, for example, think about a predictive policing algorithm. It's an algorithm that was trained to recognize, basically trained on data that says whereabouts are arrests being made. And then as you train that algorithm based on where arrests are being made, then you put in place a system that sends police officers to places that the model says are likely to have crime, which in this case, where were arrests. So then more police go to that place, find more crime, because the more police that are there, the more they'll see. They arrest more people, causing, and then if you do this incremental learning, like we're just talking about, then it's going to say, oh, there's actually even more crime here. And so tomorrow it sends even more police. And so in that situation, you end up like the predictive policing algorithm ends up kind of sending all of your police to one street block, because at that point, all of the arrests are happening there because that's the only place you have policemen, right? I should say police officers. So there's actually a paper about this issue called To Protect and Serve. And in To Protect and Serve, the authors write this really nice phrase. Predictive policing is aptly named. It is predicting policing, not predicting crime. So if the initial model was perfect, whatever the hell that even means, but like it somehow sent police to exactly the best places to find crime based on the probability of crimes actually being in place, I guess there's no problem, right? But as soon as there's any amount of bias, right? So for example, in the US, there's a lot more arrests of black people than of white people, even for crimes where black people and white people are known to do them the same amount. So in the presence of this bias, or any kind of bias, you're kind of like setting off this domino chain of feedback loops where that bias will be exploded over time. So, one thing I like to think about is to think like, well, what would happen if this model was just really, really, really good? So like, who would be impacted? What would this extreme result look like? How would you know what was really happening? This incredibly predictive algorithm that was like changing the behavior of your police officers or whatever. What would that look like? What would actually happen? And then like think about like, okay, what could go wrong? And then what kind of rollout plan, what kind of monitoring systems, what kind of oversight could provide the circuit breaker? Because that's what we really need here, right? Is we need, like, nothing's going to be perfect. You can't be sure that there's no feedback loops. But what you can do is try to be sure that you see when the behavior of your system is behaving in a way that's not what you want. Did you have anything to add to that, Rachel?
All I would add to that is that you're at risk of potentially having a feedback loop anytime that your model is kind of controlling what your next round of data looks like. And I think that's true for pretty much all products. And that can be, I think, a hard jump from people coming from kind of a science background, where you may be thinking of data as I have just observed some sort of experiment, whereas kind of whenever you're building something that interacts with the real world, you are now also controlling what your future data looks like based on kind of the behavior of your algorithm for the current round of data.
Right. So so given that you probably can't avoid feedback loops, the thing you need to then really invest in is the human in the loop. And so a lot of people like to focus on automating things, which I find weird. If you can decrease the amount of human involvement by like 90%, you've got almost all of the economic upside of automating it completely, but you still have the room to put human circuit breakers in place. You need these appeals processes, you need the monitoring, you need humans involved who kind of go, hey, that's weird. I don't think that's what we want. Okay. Yes, Rachel.
And just one more note about that. Those humans, though, do need to be integrated well with kind of product and engineering. And so one issue that comes up is that in many companies, I think that ends up kind of being underneath trust and safety, handles a lot of sort of issues with how things can go wrong or how your platform can be abused. And often trust and safety is pretty siloed away from product and eng, which actually kind of has the control over these decisions that really end up influencing them. And so having
the engineers probably consider them to be pretty annoying a lot of the time, huh? They get in the way of them getting software out the door.
Yeah, but like the kind of the more integration you can have between those, I think it's helpful for the kind of the people building the product to see what is going wrong and what can go wrong.
If the engineers are actually on top of that, they're actually seeing these things happening, then it's not some kind of abstract problem anymore. So, at this point, now that we've got to the end of chapter 2, you actually know a lot more than most people about deep learning, and actually about some pretty important foundations of machine learning more generally and of data products more generally. So now's a great time to think about writing. Sometimes we have a formatted text that doesn't quite format correctly in Jupyter Notebook, by the way. It only formats correctly in the book. So that's what it means when you see this kind of pre-formatted text. So the idea here is to think about starting writing at this point before you go too much further. Rachel.
Oh, there was a question.
Oh, okay. Let's hit the question.
Question is, I assume there are fastai type ways of keeping a nightly updated transfer learning setup. Could there be one of the fastai version 4 notebooks have an example of the nightly transfer learning training like the previous person asked? I would be interested in knowing how to do that most effectively with fastai.
Sure. So I guess my view is there's nothing fastai specific about that at all. So I actually suggest you read Emmanuel's book, that book I showed you, to understand the kind of the ideas. And if people are interested in this, I can also point you at some academic research about this as well. There's not as much as there should be, but there is some good work in this area. Okay, so the reason we mention writing at this point in our journey is because things are going to start to get more and more heavy, more and more complicated. And a really good way to make sure that you're on top of it is to try to write down what you've learned. So sorry, I wasn't sharing the right part of the screen before, but this is what I was describing in terms of the pre-formatted text, which doesn't look correct. Rachel actually has this great article that you should check out, which is why you should blog. And I will say it sort of her saying, because I have it in front of me and she doesn't, weird as it is. So Rachel says that the top advice she would give her younger self is to start blogging sooner. So Rachel has a math PhD, and this kind of idea of like blogging was not exactly something I think they had a lot of in the PhD program. But actually it's like, it's a really great way of finding jobs. In fact, most of my students who have got the best jobs are students that have good blog posts. The thing I really love is that it helps you learn. By writing down, it kind of synthesizes your ideas. Yeah, there's lots of reasons to blog. So there's actually something really cool I want to show you. Yep.
I was also just going to note, I have a second post called Advice for Better Blog Post. That's a little bit more advanced, which I'll post a link to as well. And that talks about some common pitfalls that I've seen in many blog posts, and kind of the importance of putting the time in to do it well, and some things to think about. So I'll share that post as well.
Thanks, Rachel. So one reason that sometimes people don't blog is because it's kind of annoying to figure out how to. Particularly because I think the thing that a lot of you will want to blog about is cool stuff that you're building in Jupyter Notebooks. So we've actually teamed up with a guy called Hamel Hussain and with GitHub to create this free product, as usual with FastAI, no ads, no anything, called Fast Pages, where you can actually blog with Jupyter Notebooks. And so you can go to Fast Pages and see for yourself how to do it, but the basic idea is that like you literally click one button, it sets up a blog for you, and then you dump your notebooks into a folder called _notebooks, and they get turned into blog posts. It's basically like magic, and Hamel's done this amazing job of this. And so this means that you can create blog posts where you've got charts and tables and images, where they're all actually the output of Jupyter Notebook, along with all the markdown formatted text, headings, and so forth, and hyperlinks and the whole thing. So this is a great way to start writing about what you're learning about here. So something that Rachel and I both feel strongly about when it comes to blogging is this, which is don't try to think about the absolute most advanced thing you know and try to write a blog post that would impress Jeff Hinton, right? Because most people are not Jeff Hinton. So like you probably won't do a good job because you're trying to like blog for somebody who's got more expertise than you. And B, you've got a small audience now, right? Actually, there's far more people that are not very familiar with deep learning than people who are. So try to think, and you really understand what it was like 6 months ago to be you, because you were there 6 months ago. So try and write something which the 6 months ago version of you would have been like super interesting, full of little tidbits you would have loved, that would have delighted you. That 6 months ago version of you. Okay, so once again, don't move on until you've had a go at the questionnaire to make sure that you understand the key things we think that you need to understand. Yeah, have a think about these further research questions as well, because they might help you to engage more closely with the material. So let's have a break, and we'll come back in 5 minutes time. So welcome back, everybody. This is a interesting moment in the course because we're kind of jumping from the part of the course which is very heavily around kind of the structure of like what are we trying to do with machine learning, and what are the kind of the pieces, and what do we need to know to make everything kind of work together. There was a bit of code, but not masses. There was basically no math. And we kind of wanted to put that at the start for everybody who's not, who's kind of wanting an understanding of these issues without necessarily wanting to kind of dive deep into the code and the math themselves. And now we're getting into the diving deep part. If you're not interested in that diving deep yourself, you might want to skip to the next lesson about ethics, where we, is kind of, that rounds out the kind of, slightly less technical material. So what we're going to look at here is we're going to look at what we think of as kind of a toy problem, but just a few years ago it was considered a pretty challenging problem. And the problem is recognizing handwritten digits. And we're going to try and do it from scratch, right? And we're going to try and look at a number of different ways to do it. So we're going to have a look at a data set called Mnist. And so if you've done any machine learning before, you may well have come across Mnist. It contains handwritten digits, and it was collated into a machine learning data set by a guy called Jan LeCun and some colleagues, and they used that to demonstrate one of the, probably the first computer system to provide really practically useful, scalable recognition of handwritten digits. Lynette 5 was a system that was actually used to automatically process like 10% of the checks in the US. So one of the things that really helps, I think, when building a new model is to kind of start with something simple and gradually scale it up. So we've created an even simpler version of Mnist, which we call Mnist sample, which only has 3s and 7s. Okay, so this is a good starting point to make sure that we can kind of do something easy. I picked 3s and 7s for Mnist sample because they're very different. So I feel like if we can't do this, we're going to have trouble recognizing every digit. So step one is to call untarred data. Untarred data is the fastai function which takes a URL, checks whether you've already downloaded it. If you haven't, it downloads it. Checks whether you've already uncompressed it. If you haven't, it uncompresses it. And then it finally returns the path of where that ended up. So you can see here, urls.mnistsample. So you can just hit tab to get autocomplete. Is just some location, right? It doesn't really matter where it is. And so then when we call that, I've already downloaded it and already uncompressed it because I've already ran this once before, so it happens straight away. And so path shows me where it is. Now in this case, path is dot, and the reason path is dot is because I've used this special base path attribute to path to tell it kind of like where's my starting point, and that's used to print. So when I go here ls, which prints a list of files, these are all relative to where I actually untarred this to. So it just makes it a lot easier not to have to see the whole set of parent path folders. ls is actually, so path is a, let's see what kind of type it is. So it's a pathlib path object. Pathlib is part of the Python standard library. It's a really very, very, very nice library, but it doesn't actually have ls. Where there are libraries that we find super helpful, but they don't have exactly the things we want, we liberally add the things we want to them. So we add ls. Right? So if you want to find out what ls is, as we've mentioned, there's a few ways you can do it. You can pop a question mark there, and that will show you where it comes from. So there's actually a library called fastcore, which is a lot of the foundational stuff in FastAI that is not dependent on PyTorch or Pandas or any of these big heavy libraries. So this is part of fastcore. And if you want to see exactly what it does, you of course remember you can put in a second question mark to get the source code. And as you can see, there's not much source code to it. And, maybe most importantly, please don't forget about doc, because really importantly, that gives you this show in docs link, which you can click on to get to the documentation to see examples, pictures if relevant, tutorials, tests, and so forth. So when you're looking at a new data set, you kind of I always start with just ls, see what's in it. And I can see here there's a train folder and there's a valid folder. That's pretty normal. So let's look at ls on the train folder. And it's got a folder called 7 and a folder called 3. And so this is looking quite a lot like our bear classifier data set. We downloaded each set of images into a folder based on what its label was. This is doing it at another level though. Well, the first level of the folder hierarchy is it training or valid? And the second level is what's the label? And this is the most common way for image data sets to be distributed. So let's have a look. Let's just create something called 3s that contains all of the contents of the 3 directory, training, and let's just sort them so that this is consistent. Do the same for 7s, and let's look at the 3s, and you can see they're just numbered. All right, so let's grab one of those, open it, and take a look. Okay, so there's the picture of a 3, and so what is that really? Well, not 3, type IM3. So PIL is the Python imaging library. It's the most popular library by far for working with images on Python, and it's a PNG, not surprisingly. So Jupyter Notebook knows how to display many different types, and you can actually tell if you create a new type, you can tell it how to display your type. And so PIL comes with something that will automatically display the image like so. What I want to do here though is to look at like how are we going to treat this as numbers, right? And so one easy way to treat things as numbers is to turn it into an array. So array is part of NumPy, which is the most popular array programming library for Python. And so if we pass our PIL image object to array, it just converts the image into a bunch of numbers. And the truth is it was a bunch of numbers the whole time. It was actually stored as a bunch of numbers on disk. It's just that there's this magic thing in Jupyter that knows how to display those numbers on the screen. So when we say array, turning it back into a NumPy array, we're kind of removing this ability for Jupyter Notebook to know how to display it like a picture. So once I do this, we can then index into that array and create everything from the, grab all the rows from 4 up to but not including 10, and all the columns from 4 up to and not including 10. And here are some numbers. And they are 8-bit unsigned integers. So they are between 0 and 255. So an image, just like everything on a computer, is just a bunch of numbers. And therefore we can compute with it. We could do the same thing, but instead of saying array, we could say tensor. Now a tensor is basically the PyTorch version of a NumPy array. And so you can see it's exactly the same code as above, but I've just replaced array with tensor, and the output looks almost exactly the same, except it replaces array with tensor. And so you'll see this, that basically a PyTorch tensor and a NumPy array behave nearly identically much, if not most of the time. But the key thing is that a PyTorch tensor can also be computed on a GPU, not just a CPU. So in our work and in the book and in the notebooks and in our code, we tend to use tensors, PyTorch tensors, much more often than NumPy arrays, because they kind of have nearly all the benefits of NumPy arrays, plus all the benefits of GPU computation, and they've got a whole lot of extra functionality as well. A lot of people who have used Python for a long time always jump into NumPy because that's what they're used to. If that's you, you might want to start considering jumping into tensor, Like wherever you used to write array, start writing tensor and just see what happens, because you might be surprised at how many things you can speed up or do more easily. So let's grab that 3 image, turn it into a tensor, and so that's going to be 3 image tensor. That's why I've got im3t. Okay, and let's grab a bit of it, okay, and turn it into a pandas data frame. And the only reason I'm turning it into a pandas data frame is that pandas has a very convenient thing called background gradient that turns a background into a gradient, as you can see. So here is the top bit of the 3. You can see that the zeros are the whites and the numbers near 255 are the blacks. Okay, and there's some white bits in the middle which are gray. So here we can see what's going on when our images, which are numbers, actually get displayed on the screen. It's just doing this. Okay. And so I'm just showing a subset here. The actual full number in Mnist is a 28 by 28 pixel square. So that's 768 pixels. So that's super tiny, right? My mobile phone, I don't know how many megapixels it is, but it's millions of pixels. So it's nice to start with something simple and small. Okay, so here's our goal. Create a model. So by model, I just mean some kind of computer program learnt from data that can recognize 3s versus 7s. So you could think of it as a 3 detector. Is it a 3? Because if it's not a 3, it's a 7. So stop here, pause the video, and have a think. How would you do it? How would you, you don't need to know anything about neural networks or anything else. How might you, just with common sense, build a 3 detector? Okay, so I hope you grabbed a piece of paper, a pen, jotted some notes down. I'll tell you the first idea that came into my head was, what if we grab every single 3 in the data set and take the average of the pixels. So what's the average of this pixel, 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 right? And so there'll be a 28 by 28 picture, which is the average of all of the 3s. And that would be like the ideal 3. And then we'll do the same for 7s. And then so when we then grab something from the validation set to classify, we'll say like, oh, is this image closer to the ideal 3s, the ideal 3, the mean of the 3s, or the ideal 7? This is my idea. And so I'm going to call this the pixel similarity approach. I'm describing this as a baseline. A baseline is like a super simple model that should be pretty easy to program from scratch with very little magic. You know, maybe it's just a bunch of kind of simple averages, simple arithmetic, which you're super confident is going to be better than a random model, right? And one of the biggest mistakes I see in even experienced practitioners is that they fail to create a baseline. And so then they build some fancy Bayesian model or some fancy they create some fancy Bayesian model or some fancy neural network, and they go, wow, Jeremy, look at my amazingly great model. And I'll say, like, how do you know it's amazingly great? And they'll say, oh, look, the accuracy is 80%. And then I'll say, okay, let's see what happens if we create a model where we always predict the mean. Oh, look, that's 85%. And people get pretty disheartened when they discover this, right? And so make sure you start with a reasonable baseline and then gradually build on top of it. So we need to get the average of the pixels. We're going to learn some nice Python programming tricks to do this. So the first thing we need to do is we need a list of all of the 7s. So remember, we've got the 7s, okay, which is just a list of file names, right? And so for each of those file names in the 7s, let's image.open that file, just like we did before to get a PIL object, and let's convert that into a tensor. So this thing here is called a list comprehension. So if you haven't seen this before, this is one of the most powerful and useful tools in Python. If you've done something with C#, it's a little bit like LINQ. It's not as powerful as LINQ, but it's a similar idea. If you've done some functional programming in JavaScript, it's a bit like some of the things you can do with that too. But basically, we're just going to go through this collection each item will become called O, and then it will be passed to this function, which opens it up and turns it into a tensor, and then it will be collated all back into a list. And so this will be all of the 7s as tensors. So Sylvain and I use list and dictionary comprehensions every day. And so you should definitely spend some time checking it out if you haven't already. So now that we've got a list of all of the 3s as tensors, let's just grab one of them and display it. So remember, this is a tensor, not a PIL image object. So Jupyter doesn't know how to display it. So we have to use a command to display it, and show image is a fastai command that displays a tensor. And so here is our 3. So we need to get the average of all of those 3s. So to get the average, the first thing we need to do is to change this so it's not a list, but it's a tensor itself. So currently, 3 tensors, 1, has a shape which is 28 by 28. So this is the rows by columns, the size of this thing, right? But 3 tensors itself is just a list. So I can't really easily do mathematical computations on that. So what we could do is we could stack all of these 28 by 28 images on top of each other to create like a 3D cube of images. And that's still called a tensor. So a tensor can have as many of these axes or dimensions as you like. And to stack them up, you use, funnily enough, stack. Right? So this is going to turn the list into a tensor. And as you can see, the shape of it is now 6131 by 28 by 28. So it's kind of like a cube of height 6131 by 28 by 28. The other thing we want to do is, if we're going to take the mean, we want to turn them into floating point values, because we don't want to kind of have integers rounding off. The other thing to know is that it's just as kind of a standard in computer vision that when you're working with floats, that you expect them to be between 0 and 1. So we just divide by 255 because they were between 0 and 255 before. So this is a pretty standard way to kind of represent a bunch of images in PyTorch. So these 3 things here are called the axes: first axis, second axis, third axis. And overall, we would say that this is a rank 3 tensor because it has 3 axes. So this one here was a rank 2 tensor. It has 2 axes. So you can get the rank from a tensor by just taking the length of its shape. 1, 2, 3. 3. Okay. You can also get that from, so the word, I've been using the word axis. You can also use the word dimension. I think NumPy tends to call it axis, PyTorch tends to call it dimension. So the rank is also the number of dimensions, ndim. So you need to make sure that you remember this word rank is the number of axes or dimensions in a tensor, and the shape is a list containing the size of each axis in a tensor. So we can now say stacked 3s dot mean. Now if we just say stacked 3s dot mean, that returns a single number. That's the average pixel across that whole cube, that whole rank 3 tensor. But if we say mean 0, that is take the mean over this axis. So that's the mean across the images, right? And so that's now 28 by 28 again, because we kind of like reduced over this 6131 axis. We took the mean across that axis. And so we can show that image, and here is our ideal 3. So here's the ideal 7, using the same approach. Right? So now let's just grab a 3. There's just any old 3. Here it is. And what I'm going to do is I'm going to say, well, is this 3 more similar to the perfect 3, or is it more similar to the perfect 7? And whichever one it's more similar to, I'm going to assume that's the answer. So we can't just say, look at each pixel and say, what's the difference between this pixel, 0, 0 here and 0, 0 here, and then 0, 1 here, and then 0, 1 here, and take the average. The reason we can't just take the average is that there's positives and negatives, and they're going to average out to nothing, right? So I actually need them all to be positive numbers. So there's 2 ways to make them all positive numbers. I could take the absolute value, which simply means remove the minus signs. Okay, and then I could take the average of those. That's called the mean absolute difference, or L1 norm. Or I could take the square of each difference, and then take the mean of that. And then at the end, I could take the square root, which kind of undoes the squaring. And that's called the root mean squared error, or L2. So let's have a look. Let's take a 3 and subtract from it the mean of the 3s, and take the absolute value and take the mean, okay, and call that the distance using absolute value of the 3 to a 3, and that there is the number, 0.1. Right? So this is the mean absolute difference, or L1 norm. So when you see a word like L1 norm, if you haven't seen it before, it may sound pretty fancy, but all these math terms that we see, you can turn them into a tiny bit of code, right? It's don't let the mathy bits fool you. They're often like, in code, it's just very obvious what they mean. Whereas with math, you just have to learn it, or learn how to Google it. So here's the same version for squaring. Take the difference, square it, take the mean, and then take the square root. Okay. So then we'll do the same thing for our 3. This time we'll compare it to the mean of the 7s. Right? So the distance from a 3 to the mean of the 3s in terms of absolute was 0.1. And the distance from a 3 to the mean of the 7s was 0.15. So it's closer to the mean of the 3s than it is to the mean of the 7s. So we guess, therefore, that this is a 3, based on the mean absolute difference. Same thing with RMSE, root mean squared error, would be to compare this value with this value. And again, root mean squared error, it's closer to the mean 3 than to the mean 7. So this is like a machine learning model, kind of. It's a data-driven model, which attempts to recognize 3s versus 7s. And so this is a good baseline. I mean, it's a reasonable baseline. It's going to be better than random. We don't actually have to write out minus abs mean. We can just actually use L1 loss. L1 loss does exactly that. We don't have to write minus squared. We can just write MSE loss. That doesn't do the square root by default, so we have to pop that in. Okay, and as you can see, they're exactly the same numbers. It's very important, before we kind of go too much further, to make sure we're very comfortable working with arrays and tensors. And they're so similar. So we could start with a list of lists, right, which is kind of a matrix. We can convert it into an array or into a tensor. We can display it, and they look almost the same. You can index into a single row. You can index into a single column. And so it's important to know, this is very important, colon means every row, because I put it in the first spot, right? So if I put it in the second spot, it would mean every column. And so therefore, comma colon is exactly the same as removing it. So it just turns out you can always remove colons that are at the end because they're just implied, right? You never have to. And I often kind of put them in anyway because just kind of makes it a bit more obvious how these things kind of match up or how they differ. You can combine them together. So give me the first row and everything from the first up to but not including the third column. Right, so there's that 5, 6. You can add stuff to them. You can check their type. Notice that this is different to the Python, the Python type. So type is a function, just tells you it's a tensor. If you want to know what kind of tensor, you have to use type as a method. So it's a long tensor. You can multiply them by a float, turns it into a float. So have a fiddle around. If you haven't done much stuff with NumPy or PyTorch before, this is a good opportunity to just go crazy, try things out. Try things that you think might not work and see if you actually get an error message, So we now want to find out how good is our model. Our model that involves just comparing something to a mean. So we should not compare. We should not check how good our model is on the training set, as we've discussed. We should check it on a validation set, and we already have a validation set. It's everything inside the valid directory. So let's go ahead and combine all those steps before. Let's go through everything in the validation set 3 ls, open them, turn them into a tensor, stack them all up, turn them into floats, divide by 255. Okay, let's do the same for 7s. So we're just putting all the steps we did before into a couple of lines. I always try to print out shapes all the time, because if a shape is not what you expected, then you can get weird things going on. So the idea is we want some function is3 that will return true if we think something is a 3. So to do that, we have to decide whether our digit that we're testing on is closer to the ideal 3 or the ideal 7. So let's create a little function that returns, takes the difference between two things, takes the absolute value, and then takes the mean. So we're going to create this function, Mnist distance, that takes the difference between two tensors, takes their absolute value, and then takes the mean. And it takes the mean, and look at this, we've got minus this time. It takes the mean over the last, over the second last and third last, the last and second last dimensions. So this is going to take the mean across the kind of x and y axes. And so here you can see it's returning a single number, which is the distance of a 3 from the mean 3. So that's the same as the value that we got earlier, 0.1114. So we need to do this for every image in the validation set because we're trying to find the overall metric. Remember, the metric is the thing we look at to say how good is our model. So here's something crazy. We can call Mnist distance not just on R3, but on the entire validation set against the mean 3. So that's wild. There's no normal programming that we would do where we could somehow pass in either a matrix or a rank 3 tensor, and somehow it works both times. And what actually happened here is that instead of returning a single number, it returned 1010 numbers. And it did this because it used something called broadcasting. And broadcasting is like the super special magic trick that lets you make Python into a very, very high performance language. And in fact, if you do this broadcasting on GPU tensors on PyTorch, it actually does this operation on the GPU, even though you wrote it in Python. here's what happens. Look here, this a minus b. So we're doing a minus b on two things. We've got, first of all, valid 3 tens. So valid 3 tensor is 1,000 or so images, right? And remember that mean 3 is just our single ideal 3. So what is something of this shape minus something of this shape? Well, broadcasting means that if this shape doesn't match this shape, like if they did match, it would just subtract every corresponding item. But because they don't match, it actually acts as if there's 1,010 versions of this. So it's actually going to subtract this from every single one of these, right? So broadcasting, let's look at some examples. So broadcasting requires us to first of all understand the idea of element-wise operations. This is an element-wise operation. Here is a rank 1 tensor of size 3 and another rank 1 tensor of size 3. So we would say these sizes match, they're the same. And so when I add 1, 2, 3 to 1, 1, 1, I get back 2, 3, 4. It just takes the corresponding items and adds them together. So that's called element-wise operations. So when I have different shapes, as we described before, what it ends up doing is it basically copies this number 1,010 times. And it acts as if we had said valid 3 tens minus 1,010 copies of mean 3. As it says here, it doesn't actually copy mean 3 1,010 times, it just pretends that it did, right? It just acts as if it did. So basically kind of loops back around to the start again and again. And it does the whole thing in C or in CUDA on the GPU. So then we see absolute value, right? So let's go back up here. After we do the minus, we go absolute value. So what happens when we call absolute value on something of size 10, 10 by 28 by 28? Just calls absolute value on each underlying thing, right? And then finally, we call mean. -1 is the last element always in Python. -2 is the second last. So this is taking the mean over the last 2 axes. And so then it's going to return just the first axis. So we're going to end up with 1,010 means, 1,010 distances, which is exactly what we want. We want to know how far away is each of our validation items away from the ideal 3. So then we can create our is3 function, which is, hey, is the distance between the number in question and the perfect 3 less than the distance between the number in question and the perfect 7? If it is, it's a 3, right? So for R3, that was that actual 3 we had. Is it a 3? Yes. Okay, and then we can turn that into a float, and yes becomes 1. Thanks to broadcasting, we can do it for that entire set, right? So this is so cool. We basically get rid of loops. In this kind of programming, you should have very few loops. Loops make things much harder to read and hundreds of thousands of times slower. On the GPU, potentially tens of millions of times slower. So we can just say is3 on our whole valid 3 tens, and then turn that into float, and then take the mean. So that's going to be the accuracy of the 3s on average. And here's the accuracy of the 7s. It's just 1 minus that. So the accuracy across 3s is about 91 and a bit %. The accuracy on 7s is about 98%. And the average of those two is about 95%. So here we have a model that's 95% accurate at recognizing 3s from 7s. It might surprise you that we can do that using nothing but arithmetic, right? So that's what I mean by getting a good baseline. Now, the thing is, it's not obvious how we kind of improve this, right? I mean, the thing is, it doesn't match Arthur Samuel's description of machine learning, right? This is not something where there's a function which has some parameters which we're testing against some kind of measure of fitness and then using that to like improve the parameters iteratively. We just did one step and that's that, right? So we want to try and do it in this way, where we arrange for some automatic means of testing the effectiveness of, he called it a weight assignment, we'd call it a parameter assignment, in terms of performance, and a mechanism for altering the weight assignment to maximize the performance. That we want to do it that way, right? Because we know from chapter 1, from lesson 1, that if we do it that way, we have this like magic box, right, called machine learning that can do, particularly combined with neural nets, should be able to solve any problem in theory, if you can at least find the right set of weights. So we need something that we can get better and better to learn. So let's think about a function which has parameters. So instead of finding an ideal image and seeing how far away something is from the ideal image, so instead of like having something where we test how far away we are from an ideal image, what we could instead do is come up with a set of weights for each pixel. So we're trying to find out if something is the number 3. And so we know that like in the places that you would expect to find 3 pixels, you could give those like high weights. So you can say, hey, if there's a dot in those places, we give it like a high score. And if there's dots in other places, we'll give it like a low score. So we could actually come up with a function where the probability of something being an, well, in this case, let's say an 8, is equal to the pixels in the image multiplied by some set of weights, and then we sum them up, right? So then anywhere where the image we're looking at, has pixels where there are high weights, it's going to end up with a high probability. So here X is the image that we're interested in. And we're just going to represent it as a vector. So let's just have all the rows stacked up end to end into a single long line. So we're going to use an approach where we're going to start with a vector W. So a vector is a rank 1 tensor. Okay, we're going to start with a vector W that's going to contain random weights, random parameters, depending on whether you use the Arthur Samuel version of the terminology or not. And so we'll then predict whether a number appears to be a 3 or a 7 by using this tiny little function. And then we will figure out how good the model is. So we will calculate like how accurate it is or something like that. The loss. And then the key step is we're then going to calculate the gradient. Now the gradient is something that measures for each weight. If I made it a little bit bigger, would the loss get better or worse? If I made it a little bit smaller, would the loss get better or worse? And so if we do that for every weight, we can decide for every weight whether we should make that weight a bit bigger or a bit smaller. So that's called the gradient, right? So once we have the gradient, we then step, it's the word we use, a step, we change all the weights up a little bit for the ones where the gradient said we should make them a bit higher, and down a little bit for all the ones where the gradient said they should be a bit lower. So now it should be a tiny bit better. And then we go back to step 2 and calculate a new set of predictions using this formula. Calculate the gradient again, step the weights, keep doing that. So this is basically the flow chart. And then at some point, when we're sick of waiting or when the loss gets good enough, we'll stop. So these 7 steps, 1, 2, 3, 4, 5, 6, 7, these 7 steps are the key to training all deep learning models. This technique is called stochastic gradient descent. Well, it's called gradient descent. We'll see the stochastic bit very soon. And for each of these 7 steps, there's lots of choices around exactly how to do it, right? We've just kind of hand-waved a lot, like what kind of random initialization and how do you calculate the gradient and exactly what step do you take based on the gradient and how do you decide when to stop, blah, 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 right? So in this course, we're going to be like learning about, these steps. That's kind of part 1. And then the other big part is like, well, what's the actual function? Neural network. So how do we train the thing and what is the thing that we train? So we initialize parameters with random values. We need some function that's going to be the loss function that will return a number that's small if the performance of the model is good. We need some way to figure out whether the weight should be increased a bit or decreased a bit. And then we need to decide like when to stop, which we'll just say, let's just do a certain number of epochs. So let's like go even simpler, right? We're not even going to do Mnist. We're going to start with this function x squared. Okay, and in fastai we've created a tiny little thing called plot function that plots a function. All right, so there's our function f, and what we're going to do is we're going to try to find, this is our loss function, so we're going to try and find the bottom point, right? So we're going to try and figure out what is the x value which is at the bottom. So our 7-step procedure requires us to start out by initializing. So we need to pick some value, right? So the value we pick, we just say, oh, let's just randomly pick -1.5. Great. So now we need to know if I increase x a bit, remember this is my loss, does my loss get a bit better? Remember, better is smaller, or a bit worse. So we can do that easily enough. We can just try a slightly higher x and a slightly lower x and see what happens, right? And you can see it's just the slope, right? The slope at this point tells you that if I increase x by a bit, then my loss will decrease, because that is the slope at this point. So if we change our weight, our parameter, just a little bit in the direction of the slope, right? So here is the direction of the slope. And so here's the new value at that point, right? And then do it again, and then do it again. Eventually, we'll get to the bottom of this curve, right? So this idea goes all the way back to Isaac Newton, at the very least. And this basic idea is called Newton's method. So a key thing we need to be able to do is to calculate this slope. And the bad news is, do that, we need calculus. At least that's bad news for me, because I've never been a fan of calculus. We have to calculate the derivative. Here's the good news, though. Maybe you spent ages in school learning how to calculate derivatives. You don't have to anymore. The computer does it for you. And the computer does it fast. It uses all of those methods that you learned at school, and a whole lot more, like clever tricks for speeding them up, and it just does it all automatically. So for example, it knows, I don't know if you remember this from high school, that the derivative of x squared is 2x. It's just something it knows. It's part of its kind of bag of tricks, right? So PyTorch knows that. PyTorch has an engine built in that can take derivatives and find the gradient of functions. So to do that, we start with a tensor, let's say. And in this case, we're going to modify this tensor with this special method called requiresGrad. And what this does is it tells PyTorch that anytime I do a calculation with this xt, it should remember what calculation it does so that I can take the derivative later. Do you see the underscore at the end? An underscore at the end of a method in PyTorch means that this is called an in-place operation. It actually modifies this. So requires grad underscore modifies this tensor to tell PyTorch that we want to be calculating gradients on it. So that means it's just going to have to keep track of all of the computations we do so that it can calculate the derivative later. Okay, so we've got the number 3, and let's say we then call f on it. Remember, f is just squaring it. So 3 squared is 9. But the value is not just 9, it's 9 accompanied with a grad function, which is that it knows that a power operation has been taken. So we can now call a special method backward. And backward, which refers to back propagation, which we'll learn about, which basically means take the derivative. And so once it does that, we can now look inside xt, because we said requires grad, and find out its gradient. And remember, the derivative of x squared is 2x. In this case, that was 3. 2 times 3 is 6. Right? So we didn't have to figure out the derivative. We just call backward and then get the grad attribute to get the derivative. So that's how easy it is to do calculus in PyTorch. So what you need to know about calculus is not how to take a derivative, but what it means. And what it means is it's a slope at some point. Now here's something interesting. Let's not just take 3, but let's take a rank 1 tensor, also known as a vector, 3, 4, 10. And let's add sum to our f function. So it's going to go x squared dot sum. So now we can take f of this vector, get back 125, and then we can say backward and grad, and look, 2x, 2x, 2x. Right? So we can calculate, this is vector calculus, right? We're getting the gradient for every element of a vector with the same 2 lines of code. So that's kind of all you need to know about calculus, right? And if this is, if this idea that a derivative or gradient is a slope is unfamiliar, check out Khan Academy. They have some great introductory calculus. And don't forget, you can skip all the bits where they teach you how to calculate the gradients yourself. So now that we know how to calculate the gradient, that is the slope of the function, that tells us if we change our input a little bit, how will our output change correspondingly? That's what a slope is, right? And so that tells us that every one of our parameters, if we know their gradients, then we know if we change that parameter up a bit or down a bit, how will it change our loss? So therefore, we then know how to change our parameters. So what we do is, let's say all of our weights are called W. We just subtract off them the gradients multiplied by some small number. And that small number is often a number between about 0.001 and 0.1. It's called the learning rate, right? And this here is the essence of gradient descent. So if you pick a learning rate that's very small, then you take the slope and you take a really small step in that direction. And another small step, another small step, another small step. And it's going to take forever to get to the end. If you pick a learning rate that's too big, you jump way too far each time. And again, it's going to take forever. And in fact, in this case, we're assuming we're starting here, and it was so big that it got worse and worse. Or here's one where we start here, and it's not so big it gets worse and worse, but it just takes a long time to bounce in and out. Right? So picking a good learning rate is really important, both to making sure that it's even possible to solve the problem, and that it's possible to solve it in a reasonable amount of time. So we'll be learning about picking how to pick learning rates in this course. So let's try this. Let's try using gradient descent. I said SGD, that's not quite accurate. It's just going to be gradient descent to solve an actual problem. So the problem we're going to solve is, let's imagine you were watching a roller coaster go over the top of a hump, right? So as it comes out of the previous hill, it's going super fast, and it's going up the hill, and it's going slower and slower and slower until it gets to the top of the hump, and then it goes down the other side. It goes faster and faster and faster. So if you like had a stopwatch or whatever, or some kind of speedometer, and you were measuring it just by hand at kind of equal time points, you might end up with something that looks a bit like this, right? And so the way I did this was I just grabbed a range, just grabs the numbers from 0 up to but not including 20, right? So these are the time periods at which I'm taking my speed measurement. And then I've just got some quadratic function here. I multiply it by 3 and then square it and then add 1, whatever, right? And then I also, actually, sorry, I take my time minus 9.5, square it, times 0.75, add 1, and then I add a random number to that, or add a random number to every observation. So I end up with a quadratic function, which is a bit bumpy. So this is kind of like what it might look like in real life, because my speedometer kind of testing is not perfect. All right, so we want to create a function that estimates at any time what is the speed of the roller coaster. So we start by guessing what function it might be. So we guess that it's a function a times time squared plus b times time plus c. You might remember from school is called a quadratic. So let's create a function, right? And so let's create it using kind of the Arthur Samuels technique, the machine learning technique. This function is going to take two things. It's going to take an input, which in this case is a time, and it's going to take some parameters. And the parameters are a, b, and c. So in Python, you can split out a list or a collection into its components like so. And then here's that function. Okay. So we're not just trying to find any function in the world, we're just trying to find some function which is a quadratic by finding an a and a b and a c. So the Arthur Samuel technique for doing this is to next up come up with a loss function, come up with a measurement of how good we are. So if we've got some predictions that come out of our function, and the targets, which are these actual values, then we could just do the mean squared error. Okay, so here's that mean squared error we saw before. The difference squared, and then take the mean. So now we need to go through our 7-step process. We want to come up with a set of 3 parameters, a, b, and c, which are as good as possible. So step 1 is to initialize a, b, and c to random values. So this is how you get random values, 3 of them in PyTorch. And remember, we're going to be adjusting them, so we have to tell PyTorch that we want the gradients. I'm just going to save those away so I can check them later. And then I calculate the predictions using that function f, which was this. And then let's create a little function which just plots how good at this point are our predictions. So here is a function that prints in red our predictions and in blue our targets. So that looks pretty terrible. So let's calculate the loss using that MSE function we wrote. Okay, so now we want to improve this. So calculate the gradients using the 2 steps we saw, call backward and then get grad. And this says that each of our parameters has a gradient that's negative. Let's pick a learning rate of 10 to the minus 5. So we multiply that by 10 to the minus 5. And step the weights. And remember, step the weights means minus equals learning rate times the gradient. There's one little trick here, which I've called dot data. The reason I've called .data is .data is a special attribute in PyTorch, which if you use it, then the gradient is not calculated. And we certainly wouldn't want the gradient to be calculated of the actual step we're doing. We only want the gradient to be calculated of our function f. Right? So when we step the weights, we have to use this special .data attribute. After we do that, delete the gradients that we already had, and let's see if loss improved. So the loss before was 25,800. Now it's 5,400. And the plot has gone from something that goes down to minus 300 to something that looks much better. So let's do that a few times. So I've just grabbed those previous lines of code and pasted them all into a single cell. Okay, so preds, loss, backward, data, grad is none. And then from time to time, print the loss out. And repeat that 10 times. And look, getting better and better. And so we can actually look at it getting better and better. So this is pretty cool, right? We have a technique. This is the Arthur Samuel technique for finding a set of parameters that continuously improves by getting feedback from the result of measuring some loss function. So that was kind of the key step, right? This is the gradient descent method. So you should make sure that you kind of go back and feel super comfortable with what's happened. And you know, if you're not feeling comfortable, that's fine, right? If it's been a while or if you've never done this kind of gradient descent before, this might feel super unfamiliar. So kind of try to find the first cell in this notebook where you don't fully understand what it's doing. And then like stop and figure it out. Like look at everything that's going on, do some experiments, do some reading until you understand that cell where you were stuck before you move forwards. So let's now apply this to Mnist. So for Mnist, we want to use this exact technique. And there's basically nothing extra we have to do, except one thing. We need a loss function. And the metric that we've been using is the error rate or the accuracy. It's like how often are we correct, right? And that's the thing that we're actually trying to make good, our metric. But we've got a very serious problem, which is, remember, we need to calculate the gradient to figure out how we should change our parameters. And the gradient is the slope or the steepness, which you might remember from school is defined as rise over run. It's y new minus y old divided by x new minus x old. So the gradient's actually defined when x new is very, very close to x old, meaning their difference is very small. But think about it. Accuracy. If I change a parameter by a tiny, tiny, tiny amount, the accuracy might not change at all because there might not be any 3 that we now predict as a 7 or any 7 that we now predict as a 3 because we changed the parameter by such a small amount. So it's possible, in fact it's certain, that the gradient is 0 at many places. And that means that our parameters aren't going to change at all because learning rate times gradient is still 0 when the gradient's 0 for any learning rate. So this is why the loss function and the metric are not always the same thing. We can't use a metric as our loss if that metric has a gradient of 0. So we need something different. So we want to find something that kind of is pretty similar to the accuracy in that, like, as the accuracy gets better, this ideal function we want gets better as well, but it should not have a gradient of 0. So let's think about that function. suppose we had 3 images. Actually, you know what? This is actually probably a good time to stop, because actually, you know, we've got to the point here where we understand gradient descent. We kind of know how to do it with a simple loss function. And I actually think before we start looking at the Mnist loss function, we shouldn't move on, because we've got so much assignments to do for this week already. So we've got build your web application, and we've got go step through this notebook to make sure you fully understand it. So I actually think we should probably stop right here before we make things too crazy. So before I do, Rachel, are there any questions? Okay, great. All right, well, thanks everybody. Sorry for that last minute change of tack there, but I think this is going to make sense. So I hope you have a lot of fun with your web applications. Try and think of something that's really fun, really interesting. It doesn't have to be like important. It could just be some, you know, cute thing. We've had students before, a student that I think he said he had 16 different cousins, and he created something that would classify a photo based on which of his cousins. It was for like his fiance meeting his family. You know, you can come up with anything you like. But, you know, yeah, show off your application, and maybe have a look around at what IPy widgets can do, and try and come up with something that you think is pretty cool. All right, thanks everybody. I will see you next week.